In Chapter 18, dealing with standing waves and resonance. We start with the principle of superposition. In physics, superposition is very important when we start thinking about the individual characteristics of several things that can be brought together and combined into a net effect. In the case of superposition of waves on strings, we start with two or more traveling waves on the same string. The resultant wave function is the sum of the individual wave functions. It might look something like this, where I have one wave moving to the left, to the right, and another wave moving to the left, and they maintain their individual characteristics, but at some point, like in C here, they constructively interfere and the individual characteristics cannot be determined at that moment. You just see the net effect. But a moment later, as in D, the individual waves carry on in their merry way, and you can see their individual characteristics again. So the principle of the individuality is maintained even though their resultant effect can be combined. We could get this kind of effect where two waves are interfering with each other by a string being tied to a rigid support. As the string pulse is coming in, the tension in the string will be pulling on the string and on the support itself, and it will be pulling tangentially with the string. So as the string encounters the support, there will be a pull of tension of the string on the support. And according to Newton's third law, for every action there's an equal and opposite reaction. The support will pull back in 180 degrees opposite direction. So there will be a force of the support 180 degrees opposite to whatever the wave pulse is doing as it's encountering this wall, this support. So whatever the wave pulse is doing, the external force is going to be pulling it in exactly the opposite direction. The result, the reflected pulse is exactly 180 degrees opposite in every way from the incident pulse coming into the wall. So consider two sinusoidal waves traveling in the same medium with the same amplitude, frequency, and wave number and wavelength, but they are traveling in opposite directions. So the wave pulse might look like y1 is equal to a naught sine kx minus omega t, moving to the right, and y2 is equal to a naught sine kx plus omega t, same wave, amplitude, wave number, frequency, but moving to the left. This could happen if we had a rigid support and we were to initiate wave after wave on the string and we're reflecting off the support coming back. So we have the same type of waves interfering with each other in both directions. Looks something like this. Initiate a wave pulse. It encounters the support, bounces off, and you can see that the lead part of this red wave coming in is actually inverted 180 degrees on the reflected pulse, and that's actually above the string here. And then the back portion of this wave is actually 180 degrees opposite as well. So the wave actually looks the same as it's coming back to interfere. At different times, these two waves will superimpose, and at some point they might constructively interfere, and you would have the two amplitudes added one on top of the other, and so you have momentarily at that point a wave that looks like it's twice the amplitude of the original wave. There might be a point a quarter period later when the constructive hump of one is being exactly negated by the trough of the other, and hence you got nothing at that moment. And then a little bit later, again, constructive interference in the opposite direction, where your net amplitude is twice the amplitude of the interfering waves. Let's try to look at this interference mathematically. We're going to add the two wave functions together and see what we get. So we're going to add a naught sine kx minus omega t plus a naught sine kx plus omega t. And we're going to use the trig identity where the sine a plus or minus b is equal to sine a cosine b plus or minus cosine a sine b. So expanding these two sine functions, we get that our combined wave, our superimposed wave, is a naught sine kx cosine omega t minus sine omega t cosine kx plus a naught sine kx cosine omega t plus sine omega t cosine kx. And we see that the second terms, plus and minus, will cancel out. So we're left with just a combined wave looking like 2a naught sine kx cosine omega t. So essentially we have an amplitude of a standing wave that depends on our value of x on the string. And the whole string itself continues to vibrate all the while with an angular frequency omega equal to the angular frequency of the interfering waves. So this is our standing wave equation, wave function. So we have a standing wave. The amplitude is dependent on x. It's equal to 2a naught sine kx. And at certain points, we're going to have a maximum amplitude equal to twice the amplitude of the interfering waves. And at other points, we might even have 0, depending on when sine kx is actually equal to 0. We will actually have a value of 0, which we call a node, when sine kx is equal to 0. K, as you recall, is 2 pi over lambda. So if lambda is equal to an integral number of half wavelengths, we would get in the sine function integral numbers of pi, either pi, 2 pi, 3 pi, or whatever. And the sine of pi is 0, and multiples of pi is 0. So when that happens, we will find an amplitude of 0. And that's what we call our nodes. And that will occur when x is equal to an integral number of half wavelengths. So the first one will be at 0. The next one will be at x equal to a half wavelength. Next one, x equal to a wavelength. And then x equal to 3/2 wavelengths. So every half wavelength we have a node, which means that if we saw a standing wave, between successive nodes, there is exactly half a wavelength of the waves that are going on that string. And that would be one way that we could determine the wavelength. Just set up a standing wave, measure the distance between two nodes, or the length of one lobe, if you will, and that will be half a wavelength. Likewise, we'll have antinodes, which is maxima, whenever we have a quarter wavelength spaced half wavelength apart. So it's going to be in odd integers, multiples of quarter wavelengths. So at x equal to a quarter wavelength, 3/4 wavelengths, 5/4 wavelengths, within that equation, this will give us a sine of pi over 2, a maximum value of the sine function, giving us a maximum amplitude at that point, where the amplitude will be equal to 2a naught. Note that between successive maximum antinodes, there is again a half wavelength distance between the two. So we're looking at respective n values. We got 0, and n equal to 1, n equal to 2, n equal to 3. With n equal to 1, we can see one lobe, which actually corresponds to the fundamental mode. And we're basically having just one wave interfere on itself. And so this fundamental mode is going up and down with a node at either end, and hence the whole length of that string at that moment is equal to half a wavelength. Nodes are always spaced half a wavelength apart. Antinodes, the maxima, are also spaced in successive fashion half a wavelength apart. So as I look at n equal 2, between this node and the middle node is half a wavelength. Between the middle node and the other node on the end is half a wavelength. So the length of this whole string at this moment is equal to one wavelength. We can imagine we got one wavelength, top and bottom, and it's just oscillating back and forth like this so fast that we just see two lobes there left on the string. A node and an adjacent antinode are spaced a quarter wavelength apart. Makes sense? All points of the string, though, will vibrate with an angular frequency omega, of course, according to that cosine omega t, except for the nodes, which seem to be stationary, but if you looked at the string pretty closely, you would see it vibrating very, very quickly, even though it has no amplitude. Let's try this out. Two harmonic waves traveling in opposite directions interfere to produce a standing wave pattern described by a wave function y equal to 1.5 meters sine 0.4x cosine 200t. X is in meters, t is in seconds. Determine the wavelength, frequency, and speed of the interfering waves that created this wave function. We can identify a few things on this wave function. Out front is the amplitude, and that's equal to twice the amplitude of the interfering waves. In front of the x, spatially, will always be the angular wave number, k. And in front of the time, t, will always be the angular frequency, omega. So based on this, we can find these other things, wavelength, frequency, and speed. The wavelength we can get from the angular wave number. Wavelength is 2 pi over the angular wave number k, 2 pi over 0.4, which is 15.7 meters here. The frequency is the angular frequency divided by 2 pi. 200 divided by 2 pi is 31.8 hertz. So there's our wavelength and our frequency. If we want the propagation speed of these waves, we multiply the wavelength times the frequency. So 15.7 times 31.8 gives us 500 meters per second. And that is the velocity of the interfering waves that create this standing wave. We also could have just taken our angular frequency, 200, divided by our angular wave number, 0.4, and that would have given us the velocity of propagation as well, 500 meters per second. So imagine we have the standing wave. It's oscillating like this, so fast that we see two lobes there. And we know that the distance between two successive nodes on this is half a wavelength, or the length of one lobe is half a wavelength, so that's one way we can measure the wavelength. So we know in general that the length of this standing wave on a string will be an integral number of half wavelengths, depending on how many lobes we have. That'll be the integer that we have. So we can write that the wavelength is 2 times the length of this string divided by integer n equal to 1, 2, 3, 4, and so forth. So the possible frequencies that would cause standing wave resonance will be equal to the velocity of waves on the string divided by these wavelengths that we just defined. Wavelength being 2L over n, I have that my possible frequencies are going to be n over 2L times the velocity of waves on the string. But we know from previously that the velocity of waves on the string is equal to the tension divided by the mass per length of the string. So the frequency is going to be equal to n, which is the integer, 1, 2, 3, 4, and so forth, over 2L times the square root of the tension divided by the mass per length. We can see that if we have a given setup where we've applied the tension, we have a definite string with a definite mass per length and a definite length, and all those things can be constant, and hence our frequencies are only going to depend on n. So we're going to definitely have integral number of frequencies as the value of n goes up in integers itself. We call these things harmonics. The first harmonic is the fundamental, corresponds to n equal to 1. So if I put in all the values n equal to 1, I would get the fundamental. And all the other harmonics are multiples of this fundamental. So the nth harmonic is equal to n times the first harmonic. Second harmonic is 2 times the fundamental. third harmonic is 3 times the fundamental, and so forth and so on. So these will give us all the harmonics. Let's try this out. Find the fundamental frequency and the next 3 frequencies that could cause a standing wave pattern on a string that's 30 meters long, has a mass per unit length of 9 times 10 minus 3 kilograms per meter, and is stretched to a tension of 20 newtons. Well, we know the fundamental should be 1 over 2L square root of tension over mass per length, mu. Let's put in our values. 1 over 2 times the length of the string, which is 30 meters. The tension was given as 20 newtons, and the mass per length was 9 times 10 to the minus 3 kilograms per meter. Everything is in the SI system, so our frequency is 0.786 per second, or 0.786 hertz. That's our fundamental frequency. Our next 3 harmonics. The second harmonic will be twice that, 1.57 hertz. The third harmonic will be 3 times that, 2.36 hertz. And the fourth harmonic will be 4 times that, 3.14 hertz, and so forth and so on. A little word about resonance. If you have a periodic force applied to a system and it has its own capability of a natural mode of vibration, the resulting amplitude of the motion is larger when the frequency of the applied force is equal or nearly equal to one of the natural frequencies of that system. In other words, if you have a system with natural frequency, if you come in and try to force it at that same natural frequency, you can add amplitude and energy continuously to that system. Here's how it might look. Let's say you have a forced oscillation with a definite frequency, and it happens to be equal to the actual frequency of the natural system that you're looking at. So every time you force an oscillation, it's going to add amplitude on top of the amplitude already possible in that system, and everything's going to be in sync. So every time you add an amplitude, it's just going to add to that system. An example might be, say you want to equal the frequency of a child on a swing. So a child on the swing is just like a pendulum. It's got a definite frequency associated with that action. So if you want to increase that amplitude, what you would go in is just kind of let the child swing back and forth, and then you would, on one of those oscillations, you would push right with the frequency itself and go with the push on the swing, and you would match that every time, and every time you did that, you could increase the amplitude of that child swinging on the swing. So you won't just go in there and just start pushing in the middle of a swing or in the middle of an oscillation and just go in there and start pushing. That won't work. You kind of wait until it comes in there and you just kind of match it and go with the flow. Another example, say you have Ella Fitzgerald and she's singing a note, and you wish to break a crystal glass, and to do that you have to know what the natural frequency of the crystal glass is, so that when she hits a note, she can hit that note so pure, with such a pure frequency, that you can add amplitude to that crystal, and it will gain amplitude with every oscillation of that frequency, and hence eventually shatter the glass. So it's not as important for her to sing loud as it is for her to hit the right note. If she hits a note that's a couple notes away and she's singing really, really loud, she won't shatter that glass. She has to hit the note perfectly. She has to have perfect pitch, which is why you need a good singer. And she has to continue to hit that pitch so that it can oscillate the crystal glass. You also need to use good crystal, unfortunately, because you need glass that would have a good natural frequency. If you have just any old glass, it probably is pretty amorphous and has different tendencies to it, and it's probably hard to hit a natural frequency that would shatter the glass. Here's another example. A couple years ago, I heard a report that some viruses have sort of shells that would associate with their cavities a natural frequency. So there will be a natural frequency associated with the outer shell of a virus. And if you were to go in with that same natural frequency, you could oscillate that virus to resonance and hence explode the virus and kill the virus. So this would be one way, possibly in the future, that you could use a medical technique based on physics where you would just attack a virus based on its natural frequency and kill it that way, as opposed to using drugs or some other method that maybe the virus can adapt to. Just make sure if you do this that you don't have any really small turtles around that are the same size, because you don't want to hurt the turtles when you're trying to kill the virus. A real famous example of resonance is the Tacoma Narrows Bridge from 1940. This bridge was built over the Tacoma Narrows, which had a wind pattern that was very similar, and that would oscillate the bridge very similar to the natural frequency of the bridge. The bridge itself did not have much redundancy in its support. There's a suspension bridge, very simple, and it had a natural frequency on the order of a few hertz, and that just was perfect for that channel. So almost from the moment that it had been built, cars would realize that it would sway to the left and to the right. So if you drove across this bridge, you would find that it was quite a challenge to get across because it would sway you back and forth. So it earned the nickname Galloping Gertie. After 4 months or so, it reached a point where it was actually at that resonant frequency, and the wind kept on blowing at that frequency, increasing the amplitude to the point where the bridge would eventually collapse. And in this video, you can see that. There's a car that was abandoned in the middle of the bridge. Unfortunately, there was a dog in that car, and they called the local professor to go out and retrieve the dog, professor of physics, kind of with the idea, that if you understand something, a physical phenomenon, maybe you have some kind of power over it. I don't know why the professor would have to go out and do that. I don't know, but that's what he did. He tried to save the dog, and the dog refused to budge, so it went down with the car when the bridge eventually collapsed. Professor PHY214. So here's the professor walking back from the car at that moment. If this ever happens to you and you need to save a dog in a car on an oscillating bridge, don't call me. I'm not going to go out on the bridge. It's kind of like volcanologists when they have a volcano about to blow, and they know it's about to blow, and all the signs are showing that it's about to blow, and that's the time when they just want to go in and take more data close to the caldera, and it's about to blow. They don't have any power of controlling it, even though they understand the phenomena. They can't control the phenomena. They're just as susceptible as anyone else. So let's see if we can jump ahead to a point. Oops, I guess I was about to blow. So here's the car oscillating back and forth at resonance, and total collapse. Too much. It's amazing that the concrete could handle what it did, and finally the bridge collapsed. If you pass this course and become a civil engineer, don't design a bridge like this. I don't want to hear about it. They'll come back to me and ask me why you passed my course. So you want to make sure the bridge is redundant. So you have other cantilevers and support to the ground to make it redundant and make it more complicated, so it doesn't have a nice simple natural frequency like this bridge did. Okay, so that concludes our first lecture in Chapter 18 on standing waves and